You clicked on this video because you heard that half the global economy is now engaged in fossil fuel phase-out talks. That headline is compelling, but it tells you nothing about the physical reality of the transition. The real stakes are not in the negotiation rooms, but in the steel and concrete of our power infrastructure. If we cannot solve the bottlenecks of grid scale, advanced nuclear deployment, and high-voltage direct current transmission, the entire transition will stall regardless of political intent. By the end of this explanation, you will understand why the speed of our energy future is dictated by supply chain physics rather than policy slogans. The narrative of a rapid phase-out often assumes that once we decide to stop burning fossil fuels, the lights will simply switch to clean sources. This is a fundamental misunderstanding of how a modern grid operates. We are not just swapping fuel sources, we are replacing a system built on dense, dispatchable energy with one that relies on intermittent generation and massive new transmission networks. The research into depletion kinetics suggests that market forces might outpace political agreements, but that model ignores the critical infrastructure bottlenecks that determine success or failure. It is a classic case of supply-side physics clashing with demand-side engineering realities. Consider the specific constraint of high-voltage direct current transmission. This technology is the backbone required to move power from remote renewable farms to population centers. However, the deployment rate of these assets lags significantly behind the rate at which we are building generation capacity. Data indicates that transmission asset deployment trails generation by 3 to 5 years. This creates a phenomenon engineers call a congestion tax. Even if we build all the wind and solar farms the world needs, the power cannot reach the people who need it because the transmission lines do not exist yet. This lag is not a political delay, it is a manufacturing and construction reality that creates a hard ceiling on how fast we can transition. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This lag is compounded by the fact that the exposure to the transition is not uniform across the global economy. While headlines speak of half the global economy, the critical failure points exist in specific industrial clusters. These are areas where electrification requires synchronous grid upgrades that current utility planning models fail to capture. A factory cannot simply turn on an electric furnace if the local grid cannot handle the sudden surge in load without triggering cascading failure modes. The grid stability is fragile, and without massive battery storage or firm nuclear baseload to absorb the shock, the system forces a rollback of phase-out targets. The physics of the grid demands firmness, and intermittent renewables alone do not provide it. This brings us to the second major bottleneck: advanced nuclear deployment. We often talk about nuclear power as a regulatory hurdle, but the real constraint is a non-political supply chain depth issue. The fabrication of reactor pressure vessels and specialized high-voltage switchgear creates a hard physical ceiling on transition velocity. You cannot build a reactor faster than you can cast the steel and manufacture the switchgear. These components require specialized foundries and a workforce with decades of experience. The supply chain for these critical components is thin, and expanding it takes years. Even if every government approved a nuclear program tomorrow, the physical capacity to build the reactors is limited by the availability of these specific industrial inputs. The interplay between these constraints creates a complex trade-off landscape. Engineering decisions in the transition prioritize grid stability over speed. The most viable path forward is not building new generation in isolation, but retrofitting existing transmission corridors for bidirectional flow and integrating advanced inverter-based resources. This is a more difficult and less glamorous task than breaking ground on new power plants. It requires upgrading the digital and physical controls of the grid to manage the flow of energy from thousands of distributed sources. Without this retrofitting, the grid cannot absorb intermittent generation without risking blackouts that force a return to fossil fuels. The absence of data on grid capacity limits in many current models reveals a significant knowledge gap. We have good models for how fossil fuel reserves deplete, but we lack precise quantification of how much transmission capacity is needed to integrate firm low-carbon baseload power. This uncertainty makes planning incredibly difficult. We are essentially trying to build a new global nervous system while the body is still running on the old one. The risk is that we build generation capacity that cannot be utilized because the transmission network is saturated, leading to a situation where we have the power but cannot use it. This reality shifts the focus from political timelines to hard engineering constraints. The transition is not a matter of will, it is a matter of material throughput. We are constrained by the rate at which we can mine, refine, and fabricate the materials needed for the new grid. The depletion of fossil fuels is a natural process, but the construction of the replacement infrastructure is a human process limited by our industrial capacity. If we cannot match the rate of construction to the rate of retirement, the transition will stall. The physical reality of energy density and transmission infrastructure will dictate the trajectory, not the announcements made at international summits. Ultimately, the success of the phase-out depends on solving these physical bottlenecks. We need to accelerate the deployment of high-voltage direct current lines to clear the congestion tax. We must expand the supply chains for nuclear components to remove the fabrication ceiling. And we must prioritize grid stability through advanced inverters and storage to ensure the system can handle the intermittency of renewables. Only by addressing these hard engineering constraints can we move beyond slogans and achieve a functional, low-carbon energy system. The transition is happening, but it is being driven by the limits of our industrial capacity, not the speed of our political will. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.